Hello everyone. So we are going to be finishing up the Houdini portion of the cloud simulation in this episode. This is just going to be pretty quick. We're just going to be working through adding disturbance, which is this detailed breakup on the surface of these clouds, and a little bit of dissipation to kind of keep their shapes controlled a little bit, and then cleaning up some of the ugly bits, particularly around the bottom. So this should be pretty quick, and we are definitely out of the jungle when it comes to the simulation stuff. So if you followed the last tutorial successfully, this should be a really fun little breeze for you. Anyways, let's go into Houdini. Alrighty, so in Houdini, this is where we left off. We had our base clouds bubbling up, but we don't really have any details going on in the these convective regions and such, where we would normally see like some noisiness and as I mentioned before, like the breakup that you get when you look at real clouds. But our shapes look nice and they move pretty well. So let's start by adding in some disturbance. And this disturbance is essentially just microturbulence, which means that it's going to break up these smooth bits and give them a lot more apparent detail. So I'm going to reset our simulation. So how we're going to be implementing our disturbance is we're going to be using this advection input of the smoke solver. And we're going to be essentially attaching a noise force to this. And that noise force is going to sort of jitter the tops of the clouds a little bit, and it'll make them have a lot more, as I mentioned before, apparent detail. So how are we going to add in a noise force? And by the way, for those of you that know Houdini, there is a gas disturb node, and this does essentially do a similar thing, but it doesn't give us necessarily the control and sort of lower level access that I want to use here. So we're going to be using noises in VOPs, sort of like what we did up here in this load texture thing, right? How we're using this noise to break up the texture a little bit. So let's add in a gas field VOP. And then connect the output of this to the advection input here. I'm just going to call this disturbance. Fantastic. So now when we go in this VOP, we can see we have the density of from this volume VOP global connected to the density of this volume VOP output. But instead of instead of affecting the density, we need to be affecting the velocity, because the forces act on the velocity. If you know physics, right? The force is the change, the change of momentum, right? And the momentum is the velocity times the mass. In VFX, we don't necessarily consider the mass when we're just dealing with smoke simulation, so we're just saying the change of the velocity. So we need to use a bind node, and we're going to bind the vel field, and vel is our velocity field. And we importantly need to set the type to 3 floats, because our vel exists in like sort of, what doesn't exist? It contains information for the velocity of each direction. I'm going to copy this and paste it. And in the second one, I'm going to say use this node to set parameter attributes, and then set this export to when input is connected. And then we're going to connect this up like that. So hopefully the explanation regarding we're messing with the velocity makes sense. We wanted to sort of, add some noise to the velocity so that the smoky, bubbly bits get broken up a little bit more. I know it's a little bit hard to grasp if you don't do this all the time. And some feedback on my last video was that it wasn't necessarily intuitive, which I did my best, but I do think if you're new at Houdini, this is definitely, there's just no two ways around it. This is a little bit new. Anyways, let's add in an anti-alias noise. And we're just going to start by connecting this up to the position. And we want to set the signature up here to 3D input and 3D noise, because our velocity is a 3-dimensional vector, right? So we want to also use the 3D output of the noise, right? So this will generate noise independently in the red, green, and blue, or X, Y, and Z channels. And then we're going to add an add node. And here I'm just going to put in a multiply constant node. And we want to just verify that what we're doing here actually works. So I'm going to compute a few frames. I'm actually going to set the value in this mul const here, the multiply constant, to like 5, just so you can see it a little bit easier. Alrighty, so I simulated a couple frames. I actually had to turn this up to 25 to get a better, to get a more visible result. And you can see we're definitely getting a lot more like a noisy result, as you can see here. But the tips of our little cloud balloons here, they're not being affected too much, but we can at least see something is happening on these lower ones. And I'm going to go into my display options because this volume filtering thing is bugging the heck out of me. So in the geometry tab up here, I'm going to set the volume filtering to off. That's just going to be a little bit easier. And I'm also going to, in the texture settings, by default, the Houdini viewport will limit the resolution. Usually it's limited to like 128, I think. I'm going to set mine up to 1024 by 1024 by 1024 and just leave it there because I want to see as much detail as possible. So yeah. So this is definitely a bit of an issue where we're getting disturbance in these bits where we don't really want all that much disturbance, but we're getting virtually none up here. So what do we do about that? So we're going to tie our disturbance to the upward velocity at the point that we're adding the disturbance to. So we're going to, because we want these more convective bits, these more buoyant bits, they're experiencing a lot more of the forces of the atmosphere because they're pushing through it. So it can be expected that they're going to deal with more of the micro turbulence. So what we're going to do here is we're going to use a vector to float. And because y is up in Houdini, we're just going to multiply our disturbance output. I'm going to reset this, by the way. So multiplying the output of this mul const by fbel2, which is the y channel. And because these things are going to be moving up very fast, we don't really want this crazy multiplier on here. So I'm just going to delete this. I'm just going to use a regular multiply. So multiply. And then we can add in a parameter here to control the strength. I'm going to call this disturbance 1 strength. That's a bit of foreshadowing because we're going to have more disturbances than just this. So there we go. I'm going to tie that to the second input there. And I'm just going to increase the strength to like 3, and then I'm going to preview a couple frames, and let's see if this works. All right, so a couple frames in, and we see this was worked brilliantly. We are no longer getting super fuzzy bits around here, but we are getting a lot more detail in these little plumes here. But these are still overall fairly circular, and if we are spherical, and clouds aren't necessarily like fuzzy spheres bobbing up. So the reason why my Houdini is not liking that, the reason why we're using multiple disturbances, or we will be using multiple disturbances, is we want one to take care of these like kind of tiny little details, but we want the others to provide a larger shape to the clouds and break up their shape, their little globularness a little bit more. But let's finish creating this disturbance layer. before we move on to that stuff. So I want the disturbance to change over time. So we're going to be converting this to a 4D noise. So 4D noise will take a 4-dimensional vector as an input. So the first 3 channels of that vector will be the regular position input, and then the next channel will be the time. So I'm going to do a vec to vec4. And we notice that the signature of the noise has changed to 4D input 1D noise. We want to change this to 4D input 3D noise. That way we get the similar 3D output. And now we have an extra slot to add another value here. And I'm going to tie this to the frame. And then I'm going to add in a divide node. And we're going to use the second value here as our disturbance scale. So I'm going to call this disturbance 1 scale. Brilliant. Set the default to like 1. I'm going to change this to like 10 so that you guys can see kind of what this does. So we're essentially, we're dividing the coordinates, both the spatial and the temporal, by 10, which effectively scales up this noise by 10. So I'm going to compute a couple frames of this and we can see how it looks. All right, so we can see what this has done. This, instead of having a very small, like noisy output, this has broken up the shapes in a much larger way. Now this is quite drastic, but you can see why this can be useful. So ideally we'd want to turn this down quite a bit, and then use multiple different scales of disturbance. So let's reset our simulation. I'm going to change the strength back down to 1. Just both of these are going to be at 1 for now. And what we can do to add multiple layers is really simple. Oops. By the way, what happened there is I accidentally double-clicked this and previewed the internals, so just go 1 level up to get out of it. So what I'm going to do is I'm just going to delete this volume VOP output. I'm going to put this in a frame by selecting all of these and pressing Shift-O. And I'm just going to label this disturbance 1. And now we can copy this. I'm going to do 3 total disturbance layers and name these disturbance 2 and disturbance 3. Then we also need to add in new parameters for each layer. So disturbance 1 strength becomes disturbance 2 strength, and same thing for the scale. And then doing the same thing for disturbance 3. And then what we're going to do is we're just going to add all 3 of these together. So placing an add node after the multiply. So, and then connect all 3 of the outputs there. Brilliant. So now we don't want to have to go into the dot network every time we want to change these parameters. So let's add these to the simulation parameters here. And because these are explicitly parameters inside of the simulation instead of the emitter, I'm going to add in a new folder here and just call these simulation properties, and setting the folder type to simple. Then I'm going to add in a subfolder here. I'm going to call this disturbance. I need to fix my keyboard position. And then another subfolder here. I'm just going to call this disturbance 1. I'm going to set the type to collapsible because and it's simple for this disturbance thing. Collapsible just because it's a little bit cleaner. All right, so I'm going to create a float parameter. I'm just going to call this one disturbance 1 strength, and copy this to the label. I'm going to set the range to, I'll leave the range where it is. And then the defaults, I'm just going to set this to 1. And then duplicate it, and I've compressed D to duplicate this. And then disturbance 1 scale. And then if I want to duplicate this, I can press D on the folder. So I'm going to do that 2 times. And then this is going to be disturbance 2. And this is going to be disturbance 3. And then we need to update the names of the parameters accordingly. Brilliant. So now when we click apply and go back up into our null node, we scroll down, we have this simulation properties and then disturbance, and then disturbance 1, 2, and 3. And then we're going to copy these parameters and then paste them into our parameters here. So I'm going to just paste all of the strength parameters. So I'm just pasting the disturbance strength 1 a couple times. And then because our parameters have a very nice naming scheme, we can just change the numbers here. And then going back up into our simulation parameters, I'm just going to grab the scale and then do the same thing here. Brilliant. So your node tree should look something like this. 3 different disturbances all being added together, multiplied by the y value of the velocity, and then added back into the velocity. And let's change the disturbance scales to be, I like to use 1, then about 3, and then 10, and then I turn the disturbance 3 strength down a little bit and the disturbance 1 strength up a little bit. And these are roughly the parameters I've found work best. So let's see how this looks. I'm going to compute a couple frames and get back to y'all. All right, so this is what our simulation looks like now. We can see that this is much, much more detailed than what we started with. We have quite a bit of, we don't have any of the bubbly nonsense that we had before. I do think this is probably a bit strong in terms of like large scale breakup, and it probably needs a little bit more like micro scale breakup. So I'm just going to turn the disturbance 3 down and the disturbance 1 up a little bit and then resimulate it. So I'll get back to you when that's done. All right, so this is what we got from the updated simulation. Here's the parameters I ended up using. So a value of 2 on the disturbance 1 and a value of like 0.5 on the disturbance 3. And I think that this looks pretty solid. I'm not going to fuss with it anymore. I think this is more than good enough. So now we're going to move on to dissipation. So this is quite simple. Essentially why we want dissipation is that if we don't have dissipation, the simulation is just going to kind of keep on growing and such. In reality, clouds will form and then they'll dissipate quite often. And this is why it's not always cloudy, because clouds dissipate pretty quickly. So in reality, cloud dissipation and such, the like sort of optical density of the clouds is somewhat more complicated, but for our CG purposes, we don't need to go into that little level of rigor. So we're going to add another gas field VOP. And really all dissipation is lowering the density of the volume a little bit each frame. So I'm going to reset our simulation. And then we're going to connect this gas field VOP right up after the disturbance. We're just going to call this dissipation. And then all we're going to do is we're going to set, we're going to multiply this by a parameter. I'm just going to call this dissipation per frame. Make sure you have underscores there. And this is essentially what percentage of the volume is going to dissipate each frame. And then all we're going to do after this is just a complement. And complement is just 1 minus whatever the this value is. So I'm going to go up here and edit the parameter interface, and I'm just going to add in a new folder called dissipation. Set it to simple, and just add in a float parameter. And just going to call this dissipation per frame. And because 1 would be complete dissipation, because if we go into here, right, imagine this is set to 1. Complement means 1 minus this value, so it's 1 minus 1, which is 0. We're multiplying the density by 0 each frame, so that's why that's like the max dissipation that we could possibly have. We want to keep this value at 1 so that you can't go past that and create weird like negative density and whatever. So that's just handy. And then let's do this. And then click apply. And then we should see it show up here. And I'm going to keep this fairly low at like 0. We can try like 0.05-ish. I think that's pretty good. Play around with this. Different like climate conditions will mean that this has a different value and such. So it's not really an exact science. Just eyeball it if you want your clouds dissipating faster or slower. And then also another thing here is like the cooling rate. This is a form of like temperature dissipation. So I think it might be handy to sort of tie that parameter to another parameter in here. I'm just going to call this one cooling rate. And just have the default set to 0.5. And then of course we need to link these up. So I'm going to link this one up to the dissipation per frame. And then this one up to the cooling rate. And cooling rate, by the way, I forgot to do this, has the same sort of parameter or range as the dissipation, where 1 is like complete cooling. It's going to be completely cool after, I think, it's just going to be completely cool. So just keeping that in mind. The time scale that this operates on is the whatever the scene time is, so it doesn't need to be, I know this isn't like super precise or whatever. This is dissipation just per frame. I'm not going to go into like calibrating this, whatever. These are just here to give us a little bit of control. They don't need to be super scientific. If you're making like a proper tool out of this, you might want to convert this into like from the per frame to like per second, which takes a little bit of math, but it's not too crazy. If you don't care about that, ignore the last minute or so. So this should make the volumes look a little bit less bulky at the top, which is sometimes what we want. So I'm going to run a simulation, and then we're going to talk about how to clean up some of the uglier areas, specifically around the bottom, and then output our simulation results. And that will be it for the tutorial today. So a little bit quicker than last time, which is nice. So I'll be back in 1 second. Alrighty, so I've simulated this a bit more, and I'm quite happy with this. I changed the dissipation down to like 0.025 just because I think this works best. But other than that, it's the exact same. So let's focus on cleaning this up and getting it ready for export. So number one thing that I see, this is really not very dense for clouds. So we're going to want to increase the density a little bit more. And the other thing is that I'm not a huge fan of the stuff that is imported like directly from the emitter. So just this bottom little bit. It's like really weird and flat and dense and looks like a cloud pancake. So we want to get rid of that and just use sort of the cloudy bits that are above it. So we can do this in a single VOP. So we're going to add in a volume VOP and put it under the convert VDB. So let's add in a multiply node and a power node too. So we're going to start off by giving us a little bit of control over the density and sort of, well, yeah, just the overall density and such of the cloud volume. So you know the drill. We're going to add in a parameter here. I'm just going to call this density and set the default just to 1. And then in the power node, we're going to connect this up and just rename it to gamma. And then same drill with the simulation parameters, adding in a new folder. And this time I'm going to put it just all the way at the bottom. I'm just going to call this post processing. And then simple. I'm just going to add in here cloud density. Or actually, I'm just going to call this density scale. And then default just going to be 1. And then the density gamma. And keep the default also at 1. FYI, you might have to recompute the current frame that you are on when you exit it, just because the node updated. But unless you like go all the way back to frame 1, you won't lose your simulation cache. Or once you go outside of the cache. I have, by the way, just want to address this real quick. This isn't like core to the tutorial, but just for like, so I can scrub through this pretty quickly. I have my cache on this dot network set like absurdly high. Please do not set it this high. The only reason I'm setting it this high is because I have a very large amount of memory. It by default is like at 5,000 megabytes or whatever. Usually that's good. You're going to want to turn this off when you export it, by the way, because this does eat up your memory. Okay. Anyways, go to the current frame. Then we can link these up to the parameters. So what happens when we change these is, well, it obviously makes it quite a bit more dense. Oops. Meant to type in 1 there. This density gamma will sort of even out the density quite a bit over the whole volume, so this is helpful. Usually I set this a little bit below 1, because even as the clouds dissipate, the apparent like visual density doesn't go down too much. They kind of just disappear. But let's clip off this bottom bit because this definitely looks more ugly than I like. So we're gonna add another multiply node here, and we're gonna use a fit range, and then a vector to float, and then using the second output of the FL2, we can hook this up to the multiply node. And then let's add in some more parameters here. So I'm just going to copy this. I'm going to call this min height. And max height as well. And we can just play around with values that work. I think this is quite a bit better. Maybe set this like from 2 to 3. We don't want to clip off too much because these clouds are quite nice. But like, I mean, you can see by just giving them a little bit of time to like to bubble up before they appear, this can be quite nice. So I think something like this is probably best, like from 2 to 6. And let's add these as parameters in here too. So I'm just going to call this what should I call this? Min height, I think. Just keep it simple. Min height. And then max height. Then apply that. All right, and they are showing up here. So I'm just going to set these to roughly where they were before. And then just port them over. All right, so how do we get this out of Houdini? So what we can use is if you want to keep this very simple, you can use a file node. So place it down and be very careful about using this, because when you preview this, if it's connected up here and it's in write mode, this file mode here, if it says write files, you will write a file out to your disk. So I'm going to connect this up. Don't preview it yet. Be careful. Write files. Still don't preview it. Go up to this little paper icon here, and this will open up a file browser here. So what I'm going to do is I'm going to create a new folder. I'm just going to call this simulation frames. And then I'm going to type in $f.vdb. Awesome. You can also, I think, I don't use automatic, but automatic should write files if they're not there and read from them if they are already there. Not sure. Here, let's test it. So when we click this out, when we click this preview thing, we go into our folder. All right, so I'm in the tutorial folders. We see we have the simulation frames folder. And then in here, we have 72.vdb. So we can see it's pulled from the current frame. So I'm going to go to frame 48 and write this out too. Brilliant. Awesome. So let's unpreview this. So preview back this volume VOP1. I'm going to reset the simulation. So the next way to output files, and the one that I recommend, is using a file cache node. And I'm pretty sure this works on Apprentice, but if it doesn't, you can use the regular file node. What this will do is it's a little bit more optimized. You don't have to like load things into the viewport and such. When you want to save out a whole thing, you can just export a frame range. So that's what we're going to do. So we need to change the file path to explicit, and then go into our file chooser, which is the paper icon. And it's by default set to the Houdini like parent folder /geo. I'm just going to delete that geo. We're going to go into the simulation frames. And then if we click on, if we set this to $f.vdb, that will export our VDB in the same format. And then when we click save to disk, you're going to see it's going to create like this little task here. And then this window comes up, and now it's rendering out our simulation. I'm going to let this cook for a few minutes and get back to you very shortly. Alrighty, so I've let it cook for a little while. I have it paused just so that my I can record properly. But when you're done or it finishes, you can just click this interrupt, and boom, you're back in business. I forgot to turn off the cache, by the way, but it's not a super huge sim, so it didn't matter. Anyways, when we go to this file cache node, we can read this directly from the disk. And I think that looks pretty good. So one of the ways I sort of store my files is I just have all my cloud simulations just rendered to the same folder. By the way, here's what all the frames look like. You can see they're just stored as 1 to 72 in this case. Whatever, 71, 72, I guess. I don't know. So what I recommend you do is you sort of scrub through the timeline here, just using the file cache node. See which frames you like. I'd recommend sort of saving a couple of them, but unless you don't need the entire, or unless you need the entire timeline, all of these ones, there's no need to store all of these on your computer. It's just a huge waste of space, especially if you have higher res ones. So I just take the, I just take a few different frames. I usually go either like 1 every 24 frames or 1 every 60, depending on the type of simulation I'm doing, and just store that in a separate folder with, yeah, to build up a little library of clouds. But these are perfectly suitable for our little planet shots. I'd recommend you export them as high res as you possibly can. And yes, that takes a little bit of time. Personally, what I do is I just turn up the resolution and leave them to render overnight. And that usually gets me pretty high quality clouds. But yeah, so simulating these as high res as you possibly can is a good idea. But if you don't want to do that, we're going to be looking at these from like from orbit. So they don't need to be super high res. Ideally, if you could get something comparable to this, that would be good. But you probably don't even need this high of resolution. All right, everyone, if you've made it this far, thank you very much. I know Houdini can be a bit of a monster to learn in some places, but if you made it this far, you are indeed a warrior. So I want to make your life a little bit easier. I have 5 cloud VDBs in this style, like these cloud fields, linked in the description below. And this is your little treat for making it this far into the video. You can use these wherever you want, however you want. And just a note, so the free ones that you can use that are in the description are the quarter resolution versions. The half res and the full res versions are on the Patreon. The full res at the $25 tier, the half res at the $10 tier, and there are about 20 clouds on the Patreon. So this is just a little subset of those. The rest of the quarter res ones are on the $5 tier. It would mean a lot if you guys would support me there, but these free ones are here for you to use wherever you want. And the free ones are honestly usually more than enough. The full res ones are just absurdly detailed. They have like 700 million to a billion polygons, which is just crazy. I have one of them loaded up here. Like you can see, it fills the entire frame. It's actually even quite a bit bigger, and it's like it still holds up. Like you can literally, it's gonna take a little while to resolve. You can get this close to it, and it's like it's fine in 4K at that. So these are absurdly high quality, and they can definitely be very useful. These are the clouds that I use like for everything. And the collection will grow in the future as I simulate more of them. They just take a little while to simulate. So shameless plug ended. Go pick up your free VDBs in the description if you want them. I really appreciate you guys watching the video. I also have the Discord server, which I've shielded at every step of the way, but it is genuinely a great place to be. A bunch of very skilled people there, and I'd hope you guys would consider joining if you are interested. So in the next episode, we will be taking these VDBs into Blender and doing some really cool stuff there. More on that later. I will see you guys. Thank you very much. Bye.